So in our last videos, we have seen different techniques which can be used to design our CMOS logic, which included PMOS like pseudo NMOS, tri-state circuits, and clocked CMOS circuits. Now in this session, we will talk about a technique which is known as the dynamic CMOS logic circuits. The dynamic CMOS logic circuits based on the concept where it operates in two modes. The first mode is like it is a charging state, or it is also known as a pre-charging state, when our PMOS is on and our NMOS is off. Like it charges the output capacitor here, and the other one is our evaluation phase where the capacitor discharges. So हम ये कह सकते हैं कि हमारा जो प्री चार्जिंग सर्किट है ये लाइक प्री चार्जिंग मोड ऑफ ऑपरेशन एक्टिवेट तब होता है जब हमारे पास फाई सिग्नल जो है वो जीरो है. इफ वी सी हेयर इन आवर सर्किट हेयर फॉर दिस डायनामिक CMOS लॉजिक सर्किट्स, तो इसमें हमारे पास ये जो फाई सिग्नल है ये बेसिकली इस NMOS को और इस हमारे PMOS को कंट्रोल कर रहा है. इस NMOS को लाइक जब फाई सिग्नल जीरो होगा तो दिस NMOS विल बी in cutoff, so it is turned off, and phi 0 means this PMOS will be turned on. If this PMOS is turned on, it will like it is a short circuit here. The current will flow on this path here, and it will charge the C out, like it will charge the output capacitor. So it means that our output is pre-charged to VDD value, and that is through our MP coil, the transistor. So this is known as a pre-charged state when our phi level is zero here, and it charges the output capacitor. The next phase is known as the evaluation phase. In this phase, like when phi is equal to 1, it means that this NMOS is now turned on, and this PMOS is off. So what will happen is this capacitor can discharge through this NFET's logic. So हम ये कह सकते हैं कि हमारा जो कैपेसिटर है वो डिस्चार्ज हो सकता है through this NFET because this path is not clear. लेकिन जो इशू है वो ये है कि this discharging depends on our inputs like the A, B and C inputs. So our inputs control whether the output will be discharged or not. For example, in a case when like A is equal to 1, B is equal to 1 and C is not, like C is equal to 0, then this path is not clear for discharging. So the output will not discharge. And here the output represents the state of this NMOS here, because if all these inputs are 1, and then the output will be discharged to 0. So it means that this represents a valid output now. So what problem we have for this type of circuits? The issue is known as the charge sharing. And charge sharing means like in case there is no path present to this ground here to through this NMOS, the NFET logics, and through this NMOS to ground. So if there is no path available that directly connects this to ground, in that case the charge is shared between the nodes here. For example, if you see here in this circuit, we have designed a logic which is known as a NAND gate. Like this circuit here, this represents a NAND gate logic. If we observe that the circuit uses less transistors than static CMOS, like this logic implements on NAND gate, but if you have seen earlier, 3-input NAND gate uses more number of transistors as compared to this one. Because we have a pull-down network and we had earlier a pull-up network as well. 3 NMOS are required for pull-down network and 3 PMOS are required for our pull-up network. So this uses less number of transistors. And obviously, if we are using less number of transistors, the area consumption is also reduced. and the fall time and can be reduced by increasing the size of of FETs. This is what we have been studying earlier. Like if you want to reduce the fall time, or if you want to reduce the rise time, then you have to basically increase the size of our MOSFETs. Let us consider this example here of this NAND gate, and we will understand how this charge sharing happen between the nodes here. Like if we consider a point here, and then we have a node here, and then we have third node here at point like this, at this junction. So let us make some derivations, and we understand what the charge sharing is and how it affects our MOSFETs. And in dynamic CMOS logic circuits, we have to tackle the issue of charge sharing. Like in our these dynamic CMOS logic, we have to deal with the charge sharing issue. We have seen earlier, like our charge leakage reduces the output voltage that was held on our output node. But another problem occurs when our phi signal is 1. Like we are not considering a case when our phi signal was 0 and our NMOS was turned on so that there was no path to the ground. So we are considering now our clock signal phi is equal to 1. This means our, like if we have this pull down network, and we had this case here, like this phi is equal to 1. It means there is no direct current to the PMOS, but we have a direct current to this NMOS. Like this is turned on, so the current, we are assuming like the current can be discharged through this point. But there would be a charge like sharing because of the parasitic node capacitors. For example, we were considering a case where we have designed a circuit somewhat like this one here. We have 3 inputs in our pull down network. Then we have a NMOS, which is basically connected to our phi, which is equal to 1 in this case. We have these 3 inputs, and we have an output node capacitor that is present here. So this is our C out, this is our V out, that is basically positive and negative. So there are 2 different node capacitors present. Like one node capacitor is present here. This is our first node capacitor. The second node capacitor appears on this point. Like this is our second node capacitor. This is known as C1, this is known as C2. So the capacitor we have 2 different capacitors, C1 and C2. These 2 are our node capacitors. And obviously the corresponding voltages are V1 and V2 on these capacitors. So we assume that at t is equal to 0, phi is equal to 1. It means that this portion of our circuit, like this portion here, this is in cutoff, like our PMOS is in cutoff. And obviously there is no direct path between VDD and Vout so that the capacitor may get charged. So we can assume at time t is equal to 0, Vout was, like, sorry, this is represented as Vout of 0. This is charged at VDD. We are assuming that it is charged at maximum value, and we also assume the voltages at V1 and V2 are 0. They are not charged, and the voltage is 0. At this time, like at this time t is equal to 0, we can say that the charge that is present at this Q, this C out is represented by Q is equal to VDD and C out. So this is our maximum charge. So the worst case of our charge sharing occurs when our input voltages are set somewhat like A is equal to 1, B is equal to 1 and C is equal to 0. This means there is no direct path between our, like this one is our in cutoff region, this MOSFET here. If this is in cutoff region, so there is no direct path between our output node, this output node, and our ground that appears here. So in this case, there is no direct discharging to the ground, but there will be some discharging through C1 and C2. So in ideal case, what we want is that the output voltage should remain high, but that will not be the case because we have our the node capacitances which are C1 and C2. So the current will flow out of our output capacitor because our C out, the V out is higher as compared to V1 and V2. So the charge that flows out of our capacitor can be represented by, like this can be represented by I. And we can say that when this current flows, V out will decrease, and while the voltages at C1 here and C2 here will increase. And this will continue until we will get a voltage level that will be equal to V out is equal to V1, which is equal to V2, and this will be our final value that is represented by Vf. And the total charge can be written as, like the total charge Q, this can be written as C out Vf plus C1 Vf and plus C2 Vf, because we have Vf as final value on all terminals. So this will be equal to C out plus C1 plus C2 and Vf. And if we know that during the principle of charge conservation, this must be equal to an initial charge. Like this is our final charge, this must be equal to our initial charge. The initial charge was C out VDD. So if we equate these two expressions 3 and 4 here, we will get 3 and 4, we will get C out VDD, which is equal to C out plus C1 plus C2, and this is multiplied by Vf. Now we have to solve this expression for Vf because we want to know the final value. This will be equal to C out divided by C out plus C1 plus C2, and this is multiplied by VDD. And looking at this expression here, we can say that this term here is less than 1, because here we have C out and here we have a addition here in C out. So we can say, using this expression, Vf will be less than VDD. So it reduces the overall output voltage. The effect of charge sharing can be reduced by this charge sharing effect can be reduced by C out if C out is greater than C1 plus C2. So then we may ignore this expression here. If we may ignore this expression, like Vf would be approximately equal to, this would be approximately equal to VDD. So we can say we can approximate the final value to VDD, but that may not be an easy task. It is difficult to achieve the capacitor values because they are dependent on the layout sizes. So it is difficult to design a capacitor that satisfies our requirements for our final voltages in charge sharing. So this was our discussion for charge sharing. So we have seen that how charge sharing affects the MOSFETs and the operation of that MOSFET. So an advanced version of this dynamic CMOS logic circuits is known as the domino logic. In this domino logic circuit, it adds an inverter to the output, like we had seen this circuit here earlier. This circuit represents the basically represents the dynamic CMOS logic circuit, but we add an inverter at the output. When we add an inverter at the output, we can see that when our phi is equal to 0, it means Cx, our output capacitor, will be charged to VDD, it will be charged through this point. And obviously, we can say that if this is charged to VDD, our output will be 0. But during the evaluation phase, we have this phi is equal to 1, like this input, this phi circuit is equal to 1. If this is 1, this means that this NMOS will be on. So this is the same logic that we have talked about earlier. But what happens at this Cx capacitor? If this is 1, our output remains high. And if our output remains high, obviously that depends on our A, B, and C serial points. If our output remains high, our V out will be equal to 0. But in case when this goes to 0 through this path here, then Cx will be 0 and our V out will be like VDD. So this basically represents a non-inverting logic circuit, because we have seen that this dynamic CMOS represents inverted logic because we have implemented a NAND gate. For example, we can see that if we have to implement an AND gate using dynamic CMOS logic circuits, we just have to add an inverter at the output. And similarly, if we have to apply an OR gate, we just have to apply a NOT gate at the output point here. So this dynamic CMOS domino logic circuits represents the non-inverting logic. And the extended version of this domino logic circuits is the domino cascade circuits. In these domino cascade circuits, we just add up multiple stages here, and on all the stages we have the capacitor here, and in all these stages, and we have an inverter. All stages have same phi. Obviously, the controlling signal, the phi signal, is same for all these stages. And during this pre-charge state, like when our phi is equal to 0, this basically is turned on. All these MOSFETs here, these are turned on. If this MOSFETs is on, it means that the capacitors will be charged to a voltage. So all these capacitors C1, C2 and C3 here, all these are charged to our maximum value, that is VDD. And all our outputs like F1, we have F2, we have F3, all these values are 0. So what happens in the evaluation phase? Like in evaluation phase, phi will be equal to 1. That means that the chain reaction the chain goes in evaluation phase. Like this whole chain here, this goes in evaluation phase. So this is known as a chain reaction that starts from first stage to the last one. It means that this reaction, like this point here, this stage 1 here, if this is charged, then it will start depending on this input here, it will go to 0. If this goes to 0, it means that this point goes to 1. If this goes to 1, it means this path is clear now, and this can go to 0 as well. So if this goes to 0, like this current starts dropping from here, from this path here, the output will drop to VDD. So if this is 1, it means this is now clear, this is now conducting, and this stage can also go to 0, and the output F3 can go to 1. So ये हमारा एक चेन रिएक्शन है जिसमें जो फर्स्ट स्टेज से स्टार्ट होता है, और डिपेंडिंग ऑन द कंडीशन ऑफ आवर फर्स्ट स्टेज, हमारी ये जो चेन रिएक्शन बेसिकली इस तरह से मूव होना शुरू हो जाता है। एज दिस इज इंडिकेटेड हेयर, लाइक चेन रिएक्शन जो है कैन बी ब्रोकन, लाइक कहीं ना कहीं पे हमारा चेन रिएक्शन जो है वो स्टॉप हो सकता है इफ वन ऑफ आवर लाइक स्टेजेस रिमेन्स हाई। अगर किसी सिचुएशन में फॉर एग्जांपल हमारे पास यहाँ पे ये जो स्टेज है, ये जो हमारे पास इनपुट है एट दिस पॉइंट हेयर, ये हमारी इनपुट जो है ये जीरो ही रहती है, तो इट मीन्स ये वाला जो पॉइंट है ये डिस्चार्ज नहीं हो रहा इवन दो दिस टू आर डिस्चार्ज। अगर ये दो डिस्चार्ज हो भी जाते हैं तो हमारा ये वाला पॉइंट जो है ये इसको डिस्चार्ज नहीं होने देगा, तो इट मीन्स दैट दिस स्टेज रिमेन्स हाई। अब ये स्टेज हमारी चेंज नहीं हो रही, तो it means this chain reaction can be broken depending on the condition of one stage। तो इस एक स्टेज की वजह से हमारा चेन रिएक्शन जो है वो उसको कंट्रोल किया जा सकता है, that can be stopped। So there are some limitations for this domino cascade performance। First condition is the domino logic gates are specifically used in in cascades। So the other thing is the domino cascade must have evaluation interval large enough। Like for example, this evaluation interval, if this evaluation interval is not large, then one stage can stand to the maximum value. So this stage cannot fall. If this stage does not fall, the next stage from stage 4, if we have it here, that will remain high as well। So if we want all stages to fall, it means that the evaluation interval must be large। So that will allow all stages to discharge, or we can say that the output will propagate from stage 1 to the last stage। So what factors limit this evaluation interval? Like we have seen earlier, there are two different problems. One is known as charge sharing and the other one is known as charge leakage। These two are limiting factors which basically affect the interval of our evaluation phase। To overcome the issue of shorter evaluation intervals, charge keeper circuits are used। For example, we have a single FET charge keeper circuit here। हमारे पास यहाँ पे एक PMOS है जो कि हमेशा ग्राउंड से कनेक्टेड है। इफ दिस PMOS इज ग्राउंडेड, इट मींस के हमारे पास ये जो CX है ये हमेशा चार्ज्ड रहेगा, ये ड्रॉप नहीं हो सकता थ्रू लीकेज करंट। हमारे पास दो कंडीशंस हैं जहां से हमारे पास ये जो CX है ये डिस्चार्ज हो सकता है। एक कंडीशन ये है कि हमारे पास एनफेट्स सारे टर्न ऑन हो जाएं और हमारे पास एक पाथ यहाँ से बन जाए जो कि इसको यहाँ पे आपके पास ग्राउंड पाथ से लिंक कर दे और हमारा जो कैपेसिटर है वो डिस्चार्ज हो जाए। सो इट मीन्स के देयर इज अ लार्ज करंट दैट विल फ्लो फ्रॉम दिस पाथ। एंड द अदर केस इज व्हेन आवर वन ऑफ आवर एनफेट इज in cut off region, and that basically limits the flow of current through this path। So in that case, the charge sharing and charge leakage will occur। It means there is a minute current that will flow from this path to grounds। Obviously that is basically the charge sharing and charge leakage। To tackle that minute current, this weak PMOS is used so that it can keep this charge here। And the other technique that is used to charge this, to keep this charge here, is use an inverter here। Like use this inverter here so that it turns on this PMOS and then the charge basically will stay on। What happens in case when this circuit discharges from this path? अगर ये सर्किट हमारा इस पाथ से डिस्चार्ज होगा तो इट मीन्स हमारे पास ये जो CX है ये पहले VDD पे था, तो ये अब डिस्चार्ज होना शुरू हो जाएगा। When this VX basically our CX discharges, it means our VX goes low। अगर हमारे पास VX low हो जाएगी तो it means this NOT gate is now the output of this NOT gate is 1 and this PMOS will be turned off। So it means there is no link between this PMOS here. So we don't need to have a weaker PMOS. So हमारे पास यहाँ पे एक चार्ज कीपर सर्किट जो है वो बेसिकली यहाँ पे एक्ट कर रहा है, जो कि हमारे चार्ज को लीकेज, चार्ज शेयरिंग और चार्ज लीकेज से ड्रॉप नहीं होने देता, और हमारी वोल्टेज को वो होल्ड रखता है अनलेस के हमारे पास ये वाला पाथ क्लियर हो और यहाँ से डिस्चार्जिंग स्टार्ट हो जाए. So this was it for our dynamic CMOS logic circuits. We have seen two different types. One is our normal dynamic CMOS logic circuits, and the other one is our domino cascade the domino cascade circuits. And we have also seen that how our charge keeper circuits can be used to basically to keep the charge at our output nodes. So I will leave you here with a practice exercise which says that draw a circuit diagram for a dynamic logic gate. So like you have to use the dynamic CMOS logic, and obviously using minimum number of transistors. So obviously if there is a option to simplify this expression, you have to do that, and the function is given here. You just have to draw a dynamic CMOS logic gate of this expression here. So that's it for this session. I will see you in next session, inshallah.